Hello, everyone. Welcome to Matteo Pozzi's talk. He's going to tell us about using reinforcement learning to perform qubit routing in quantum compilers. And Matteo, the floor is yours.
Sure. Okay. Thank you very much. Okay, here we are. Can you guys see my screen?
Yes, it looks good.
Super. Okay, hi everybody. I'm going to talk about using reinforcement learning to achieve backend optimization, specifically in terms of routing for quantum compilers. So basically, first of all, I mean, you probably are all aware about what quantum computing is, but effectively a qubit exists as a linear superposition of two computational basis states. So, you can express it as with these following formulae. And the next sort of important concept is the quantum circuit model. So basically, qubits can be manipulated via a series of 1 and 2 qubit gates, and this is what's known as a quantum circuit. And so for the rest of the presentation, we'll only consider 2 qubit gates, because those are the ones that are most important in terms of routing. Since single qubit gates can occur at any node, and I'll explain what that means in a second. So one concept that's very important in routing is the idea of a quantum architecture. So in practice, quantum computers have a connectivity graph consisting of physical qubits or nodes and links between them. So when we design a quantum circuit, we assume that any 2 qubits can interact, but in reality, they can only interact based on the nodes that they're currently residing in, and depending on the connectivity constraints of the target quantum architecture. So swap gates can move qubits. So effectively, you can swap qubits around. And so we can swap, for example, Q0 and Q1 along the top edge that's in this simple graph. So the qubit routing problem effectively is about, we can insert swap gates to make a quantum circuit executable on any given target architecture, but we want to try and do this with as little extra depth as possible. Now, what do I mean by depth? Basically, if we look on the right-hand side, we've got a circuit that corresponds to the circuit that I showed in one of the previous slides, but with an extra swap gate, and it's that swap operation that I showed in the previous couple of slides, just inserted there. And the routing process has effectively added 1 layer to the circuit, so an extra depth of 1. And so we want to try and minimize this depth as much as possible. In this case here, it's optimal, but in other cases, things might be a bit more complex. So why is this important? Well, 2 big reasons really. So first of all, it's essential to try and make the most out of the resource-constrained device, NISQ era devices. So currently, we're sort of on the brink of the NISQ era. And the devices we have at the moment are heavily resource constrained. And so, there's the problems relating to qubit decoherence. And so basically we would try, we would like to try and make the most of those machines that we have by doing as much useful work as possible before decoherence. So that's about trying to reduce circuit depth. And so much so that in 2018, IBM offered a cash prize for the best routing algorithm. So there's definitely interest from top companies in the space. So first of all, I'll give a little introduction to what it means to do qubit routing with Q-learning. So effectively, Herbert and Sengupta wrote a paper in which they came up with a formulation for using Q-learning to do qubit routing. So the state is effectively the locations of the qubits and their process through the circuit. And an action is a parallelizable layer of swap gates. So that means a series of swap gates that can occur in parallel. So the qubits will be residing on certain nodes in the architecture. They will have some gates left to do in the circuit, and then we can do these actions, make some more gates happen, and so on. And so there's a reward issued for each gate that's made possible or scheduled effectively. And so the key issue here is that we have a combinatorial action space. So since actions are sets of swap gates, if we have a topology with n edges, then there are going to be roughly 2 to the n actions that we could choose from. And so in terms of training a neural network in a traditional sort of Q-learning approach, you'd train a neural network to approximate a quality function as a function of the state and the action, to assign a quality of being in a particular state and doing a particular action. And so this, this becomes problematic if the action space is too large. So they came up with a new learning paradigm, which is basically to just assign quality to single states. And that's that. And then we can use simulated annealing, combinatorial optimization procedure to find the best next state. And so the key assumption in their paper is that CNOT gates take no time to perform. We do one layer of gates and then one layer of swaps and then so on. And we repeat this process until the circuit is fully scheduled. So effectively, we've accounted for all of the original gates in the circuit. But in reality, the trouble is that CNOT gates do take some time to perform. And so in order to try and come up with an optimal solution, we need to think about that more carefully. But I'll talk about that more later. So in terms of the research that I've done, together with Stephen Herbert, basically we decided to start by coming up with some new learning paradigms. So we made some improvements to the original approach. So first of all, we decided to come up with a more compact distance vector representation. So effectively, in the original paper, the algorithm considers, has a sort of vector in which there's one entry for each qubit, and it's just a number of the node that it's currently residing on. And obviously, that's quite a difficult representation to learn from, because the neural network effectively has to learn sort of the structure of the architecture as well as the quality of doing different things. So instead, we simplify that by coming up with a state representation that's literally just the number of qubits, the distance I from their targets. And so that's a bit simpler, a bit easier to learn from. Initially, we made some improvements to the annealer and the static heuristics that existed in the system, and we did some hyperparameter optimization. And we effectively came up with two sort of approaches. So the first approach, and these are approaches that I looked at specifically in my university dissertation. So the one we decided to go with is the Perstate agent, so I'll focus more on that. Basically, what we do is we assign a quality to pairs of consecutive states. So in that way, we can kind of capture the semantic of a state transition without having to incorporate actions, learning about actions into the neural network. So we avoid this combinatorial action space. And so the state representation is just two distance vectors concatenated. So one of the things I looked at in my dissertation, and then we decided not to use in the sort of the final paper, but another way of looking at it is also as a sort of granular single state agent. So effectively what would happen in the original system is that we would start in one particular state, we would do a layer of swaps, and then the gates would happen instantly. Whereas we can effectively break up this state transition into a sort of three states. So we start in one state, we do the swaps, and then we perform the CNOTs, and we assign different rewards to each as if they were distinct experiences. And that helped the agent to learn a bit better. And so as you can see here in terms of this performance, so on one particular benchmark, which I won't go into too much detail because we'll look more at benchmarking later, but effectively with these kinds of improvements, the new state representation, already the average number of actions is decreased greatly. And then so the average added depth effectively, but we'll think in terms of actions for now. And so the Perstate is the best one, so that's what we decide to keep. Another key contribution is a sort of a new formulation for the reinforcement learning problem. So effectively, the key reality is that CNOT gates are not instant. CNOTs are not instant, so they take some time to execute as well. And so we need to account for this in terms of representing a realistic solution to the qubit routing problem. And the reason for that is that effectively, since they take time to perform, then we can try and schedule swaps while CNOT gates are happening in order to achieve a maximum compression of depth. And I'll give an example in a second to illustrate that clearly. But what really matters is the circuit depth. This idea of number of actions is somewhat artificial. So in terms of fair benchmarking, it's important to consider the overall depth. So if we consider the above example in terms of circuit depth overhead, then effectively there are two solutions on the right-hand side for the routing problem presented on the left-hand side. So we can do a swap between, so we do the first CNOT gate, and then we can do a swap between Q1 and Q2, or we can do a swap between Q0 and Q1. And effectively, in terms of the original formulation, they appear to be the same solution because they take one layer of swap gates. But in reality, the second solution is the one that yields the lower depth. And so the reinforcement learning system needs to try and take this into account. It needs to know which gates are currently ongoing for a particular time step and what swaps can be scheduled without conflicting with them. And so we came up with this idea of protected nodes. Effectively, gates are scheduled explicitly, CNOT gates in the original circuit, that is, and they take one time step to complete. And nodes are nodes involved in the gates that are protected in the particular time step, they cannot be affected by swaps. And so swaps will be selected to be performed on any nodes not in the protected set. And we made a couple of other changes also to the reward and the state representation. Basically, as you scale up the size of the architecture, you need to start delivering some reward also for just reducing distances rather than doing gates, because sometimes the nodes involved in a particular gate can be quite far from each other, and so that reward will get heavily diluted by the sort of exponential decay factor in the Q-learning paradigm. So that's another sort of thing to bear in mind. So in terms of the performance evaluation of the system, in the paper we take a look at comparing against Qiskit, specifically the stochastic swap algorithm from IBM, Ticket as well from Cambridge Quantum Computing, and Circ as well, which is something provided by Google. So the first sort of idea is the single full layer circuit. So effectively we have one single layer of disjoint CNOT gates that, maybe on a grid architecture, you could in theory schedule with the correct initial placement all in one go in the first time step. But instead, with the random placement pictured in the middle, effectively you can only schedule the gate between Q2 and Q3. The rest, swaps will need to be inserted for that given initial placement. And so on the right-hand side, you can see a little bit how the different systems scale. So I think Circ is a reasonably naive method, at least the one that they've released publicly open sourced. And so it doesn't scale very well at all, and it performs reasonably poorly in terms of circuit depth overhead. So that means how much extra depth you need once the swaps are inserted for a given initial placement. Ticket and Qiskit both performed quite well. So in this case, I tried reproducing the results. So CQC published a paper in which they performed a similar experiment. So that's the result in orange. I tried reproducing the results myself, and that was the result in red. So slight discrepancy there, but the scaling is all very positive for those systems that I compare, except Circ, which scales a bit poorer than the rest. But Qiskit is particularly good in this situation. If Qiskit's method seems to be effectively the algorithm is stochastic, so it tries to come up with a sort of randomized layout that allows the next layer of gates to be scheduled immediately all in one go. And so, by trying to exhaustively find those over a repeated number of trials, effectively you can imagine that for a single full layer circuit, it's going to be really quite good, but that doesn't necessarily translate to, for example, random circuits. So random circuits are effectively circuits in which we just generate a random series of gates. And so here are some of the results for my system, Ticket and Qiskit. And so if we generate just a random series of gates on different size grids and on the IBM Q20 Tokyo as well, quite interestingly, my system is able to outperform the other baselines, which is very encouraging for a reinforcement learning approach, especially considering that this idea of a combinatorial action space is also quite novel. There's not really many solutions that can deal with that effectively, so that's quite encouraging. And as you can see, Qiskit starts to worsen a little bit here, particularly because it deals with single layers, and in random circuits, the layers start to become quite sparse. So the layers are not all fully occupied. And so you can imagine that an algorithm that deals with the circuit layer by layer clearly is not going to be optimal. So that's quite an interesting result. And also, if we start looking at some realistic circuits, it's quite encouraging also to see that basically the sort of deep Q learning system is able to keep up its good results in terms of circuit depth ratio now. So that's just the ratio of the output depth to the input depth, output being the circuit with the swaps inserted. But Qiskit here goes to the back of the queue effectively. And it's quite interesting to see that actually, so Ticket is proprietary, so it's closed source. So there's not much information on how it works publicly, but it would seem that it performs better on realistic circuits, which is encouraging because those are circuits that people are generally actually going to run on a target machine. So it's nice to see the increased performance there. I'd also draw your attention to the Rigetti 19Q acorn in the top right-hand corner. So in that case, the gap between my system and the others narrows. If you have a look at the paper, there's more explanation on those results. But effectively, the Rigetti 19Q acorn is quite a poorly connected architecture with not many links. And that is one of the drawbacks of my system, is that it doesn't deal as well with those architectures. Although, that said, we can reasonably assume that in future connectivity will only increase. In general, I think that's probably going to be the case. So that's one thing to consider, but that's just something to bear in mind. So before we move on to discussion of future work, in the paper, we also did a little sort of investigation towards the end, in which we basically had a look at decomposing the swap gates into CNOTs. So a swap gate can be decomposed into 3 CNOT gates. And if we perform this decomposition, then, in order to realistically run on nowadays architectures, that's a decomposition that needs to be done, because the native gate set for most quantum architectures nowadays is just CNOT gates. So swaps need to be decomposed. But it's an interesting thing to see, because actually, I'll just bring you back to a couple of these graphs. So in terms of the random circuit performance, if we do it, let's say, on a 7x7 grid with swap gates decomposed, without any other optimizations done, but we do the decomposition, then the ordering of the systems remains largely the same. So I haven't got the graphs up here now, but effectively, if you look in the paper, the deep Q-learning system is still the best in terms of circuit depth ratio, and then Qiskit, and then Ticket. However, in terms of realistic circuits, the order is actually jumbled up a little bit. So Ticket becomes the best, Qiskit becomes the next best, and my system drops to last place. And there are many reasons for this, possible reasons. So first of all, it's important to note that our research is not optimized with this in mind. We just thought it would be interesting to give it a go, to navigate some future work, and to see what can be done. And I think it basically comes down to the fact that the Q-learning system does not assign a penalty to redundantly scheduling gates in gaps in the circuit. So if there are, excuse me, if there are CNOT gates occurring in a particular time step, then even scheduling swaps that are redundant, there's no penalty for that, because the assumption with my system is that CNOT gates take as long as swaps. However, in reality, swap gates take 3 times as long. And so if the system, it's quite a simple change, but if the system was to be aware of that time constraint, then I think it would perform much better in that department. But that's just something to consider when considering, realistic machines. We decided to consider swaps and CNOTs to take the same amount of time, mainly because that's the most architecture agnostic way of doing it. But it's worth looking at those results as well. So in terms of discussion and future work, overall the system, in terms of considering CNOTs and swaps to take the same amount of time, it performs it outperforms the baseline systems on the most pertinent benchmarks, being random and realistic circuits, which give a good indication of the kinds of circuits that the routing algorithm will have to tackle. And there's an argument to be made also that it's more adaptable to new architectures. So, there's plenty of hyperparameters that can be optimized. Each time you train the system, you train it once for a particular architecture. And so, it will be specifically trained for each different architecture. And so hopefully the system is able to learn some of the nuances of different types of connectivity graphs. So in terms of future work, I think it would be nice to do a bit more feature engineering, a better state representation. So to start looking at, if we can maybe have a think about paths that might cross. So in the paper, we talk about, as a potential future optimization, having a look at if 2 nodes are quite far apart and they need to come together to do a gate, then whether there are any other nodes whose sort of shortest path might conflict, and ways in which you can represent that in the features. Also, it would be good, at the moment the training is somewhat manual, we sort of monitor it and see where the performance starts to level off in training, whereas instead it would be good to see when the weights of the neural network converge. There are also plenty of runtime improvements that can be made. So the runtime of the system is reasonably poor when you compare it to something like Ticket, which is lightning fast, or Qiskit, which is also reasonably fast. But at the same time, we did not try to optimize for runtime at all. So there's plenty of things that can be done. You can optimize the annealer, maybe use something like random restart hill climbing, even different combinatorial optimization procedures. And yeah, so there are a few things that can be done there. And also, there are other ways in which the RL paradigm can be extended for example, to include a certain type of gate called bridge gates. So effectively, these are gates in which a CNOT can occur effectively, if you have sort of 3 qubits in a row, then a bridge gate allows a CNOT gate to occur, bridging over the qubit in the middle, so the two outer qubits can interact. And so that's something that, you know, we could work to include, or also we could start to consider, you know, the fact that the swap gate takes 3 times as long as a CNOT gate, and we can look towards that sort of optimization. So that's yeah, plenty of future work to be done there, and lots of new ideas to explore. But yeah, thank you very much for listening. And I don't know if now we have the opportunity for questions, or yeah, cheers.
Hi, Matteo. Thanks a lot for the great talk. We do have a bit of time for questions. So there's a few questions on the Slack channel here that I'll ask, you know, in lieu of the actual askers. So the first one is not really a question, I guess it's more of a comment from Ross Duncan.
Yeah.
So basically his comment is that you mentioned, you know, that as technology develops, we might sort of like go towards increased connectivity. And his comment is that this might not be the case. For superconductors, it might look like, in fact, due to crosstalk, we might go towards decreased or perhaps more specialized types of connectivity.
Sure. Yeah, that's a very good point, actually. I think that's certainly possible. You know, it's difficult to tell what the future might hold. I think with any routing system, it's important to be adaptable to all kinds of situations. I think the way we've built the system, I don't think the lack of connectivity is an inherent drawback of the system. I think we just didn't, we evaluated it more on, you know, as we were developing it, we evaluated it more on things like grids or things like the IWQC20 Tokyo, you know, quite well-connected architectures. So I think it's probably optimized more in the direction of better connectivity. And so that's why it performs better on those sorts of architectures. But I don't think there are any inherent limitations in the sort of theoretical method that mean that it wouldn't be applicable to things like the Rigetti acorn. So I think future work could definitely look at trying to understand why the performance is worse. I think some of it comes from, and in the paper I talk about this, but there's, I think some of it comes from the fact that, you know, on the Rigetti acorn, since there aren't that many links, it becomes quite bottlenecked. And one issue with the system at the moment is that it's not able to distinguish between qubits of different priorities. So what I mean is, if there's one qubit that needs to interact, that let's say 10 qubits are all waiting to interact with the same one, that qubit's movement should be prioritized. But at the moment, the system has no way to distinguish between those qubits. And so I think that's definitely something that the system should try and account for in future to deal better with these kinds of bottlenecks.
I see. Yeah. Okay, great. There's another question here from Benoit Valiron.
Sure.
And he's asking, and maybe you touched upon this a little bit in your concluding remarks. He's asking, how scalable do you expect your approach to be? And in particular, you know, have you run some tests on larger architectures, like even sort of made up ones, to see how it behaves as the size of the system increases?
That's a very good point. Yeah, that's a good question. Excuse me. So yes, so we've, in the paper, we look at, I didn't show it in the presentation, but in the paper, we look at architectures up to 7 by 7. So that's 49 qubits, which is some of the larger architectures nowadays go up to roughly that size. I think Google's largest one is maybe 70 qubits, something like that. But I think recently there was an article by IBM in which they're looking to expand. So I think for all kind of for most near-term architecture sizes, I think the scaling is good. I think it would be important in future to look at the scaling of towards much larger architectures, such as 100 qubits. I think that could pose an issue. I don't think, again, I don't think the system would be inherently limited, but there could certainly be a runtime concern there, because clearly when you expand, you know, if you require a very large neural network, for example, for a much larger feature set, then that could start to pose a problem. I think in terms of the scaling we've seen so far, I think it's been quite encouraging that up to 50 qubits, it's been able to hold out quite well, and the runtime has scaled in a reasonable way. I wouldn't say it takes much longer than the smaller sizes, but that is definitely an optimization that, you know, that's an aspect that will need to be heavily optimized in order to remain competitive on the bigger architectures.
Right. Okay, got it. Thanks. And let me, there's one last question by Stefano Goggioso. So Right. So the first part of the question is that he says he's a bit unclear as to how the swaps are implemented or costed. So he's asking if you could clarify that. In particular, is it always 3 alternating C naughts? And then there's a bit of a follow-up or like an explanation for this. So for example, if you look at the 4-qubit on a line example,
Yeah.
the Q0, Q2 C naught could be more efficiently synthesized by a double ladder of C naughts rather than by introducing 3 C naughts to make a swap. So, I mean, I'm not visualizing this exact example.
Yeah. So in terms of that that second part of the question, could you just repeat exactly what's?
So the statement is, in the 4-qubit on a line example,
Yeah.
you have a Q0. So I'm guessing like between the 0th and the 2nd qubit, there's a C naught.
Exactly.
And Stefano's suggesting that it could be more efficiently synthesized by a double ladder of C naughts rather than 3 C naughts to make a swap.
Okay. So effectively, as in an alternative gate configuration that doesn't involve a swap.
I think that's what it means, yes.
Okay, sure. Yeah, so basically, what that comes down to, and I'll answer the second part of the question first. So just on that point, I think the system at the moment is constrained by the fact that it only deals with swap gates. So in the original C naughts in the original circuit need to be completed. So what I mean is, effectively, it does not consider the unitary of the circuit. It doesn't consider, equivalent gate sets or that kind of thing. It effectively sees C naught gates as, it sees C naught gates as operations that need to be completed, and swap gates as operations that allow you to move qubits. And that's, a quite crude way in which the system sees the circuit. Now, one thing we could do in future is to start looking at alternative gate arrangements. So instead of doing a swap, we might schedule an alternative action. So an action such as, 2 C naught gates in sequence that do the same thing, or maybe a bridge gate, as I was describing earlier. So what we would need to do is we would need to increase the action space, but that still fits into the RL paradigm in the sense that we can just add them as other actions that the annealer can then maybe try and select and see whether there's an increased quality state to go to. So that's that part of the question. In terms of the first part of the question, so at the moment, a swap gate is not costed in any way. So the way it works is effectively in terms of Q learning, we will see whether, let's say in the first state with the random initial placement or a particularly selected initial placement if we want. That's fine as well. Effectively, the C naught gates that can immediately occur because the qubits are adjacent, those happen straight away. They're immediately scheduled, and they become part of this protected set of nodes. And then swap gates are basically scheduled, in parallel with these C naught gates in the beginning, to try and yield, a higher quality next state. And so there's no sort of penalty associated with taking with swap gates. You can take as many swap gates as, the system is free to select as many as it wants. The function that it's trying to look towards is the quality function. So based on the current state of the locations of the distances of qubits to their targets, that's what the neural net uses to assign quality to a particular state or pair of states. And so exactly, so the way in which we would look towards allowing for this 3 time step cost for a swap, the way we would look towards accounting for that in future is effectively by saying, okay, when the system schedules a swap between 2 nodes, then those pair of nodes are protected for 3 time steps. And so the system, it takes away a degree of freedom from the system, but it doesn't really give an explicit mathematical cost. It just constrains the choices that the system can make, if that makes sense.
Yeah. Okay, great. Thanks a lot for a great talk. And
cheers, thank you.
See you soon.
Yeah, take care. Thank you so much.